Okay, today we're going to go over properties of rational functions, more specifically how to find asymptotes of rational functions. Now, a rational function is one where we divide two polynomials, p and q here, represent two different polynomials. We already learned in previous chapter how to find the domain of a rational function. Remember, the denominator can never equal 0. But today we're going to concern ourselves about is actually trying to find properties of rational functions so that we can graph them later on. So the main topic for today is how to find asymptotes. Now, an asymptote it's basically a line that a curve approaches okay. It's basically a line that a curve approaches and does not cross for a finite distance. Okay? It's a line that a curve approaches and does not cross for a finite distance. So what does that mean? What does it look like? Well, when I graph something, so let's pretend this is my coordinate plane. I could have what are called asymptotes. They are imaginary lines that my curve will not intersect. So for example, my rational function could look like something like this. Okay. These are asymptotes. Those little dashed lines that I just drew in, they're values where the curve will never touch. The curve will never touch this line, the curve will never touch that line, and so forth. We're going to concern mainly ourselves today with vertical asymptotes and horizontal asymptotes and how to find them. Now, although asymptotes are what I just defined as lines that the curve does not cross, there is a possibility that you can cross a horizontal asymptote. Okay. There is a possibility you can cross a horizontal asymptote. The reason being is that the horizontal asymptote will only be an asymptote for the left side and the right side of this graph. In the middle, it doesn't act as an asymptote. Okay, we don't have to worry about that too much right now, but the vertical asymptotes are basically ones that you definitely can't cross. Horizontal asymptotes, yes. And before we get started in how to find asymptotes, there is a third type of asymptote. It is called oblique asymptote, which is basically, instead of a horizontal or vertical line, it's a line with the equation y is equal to mx plus b. And for example, your curve will not cross that line. Okay, that's an oblique asymptote, and we're not going to concern ourselves with that for right now. So how do I find a vertical asymptote? Okay. Basically, to find a vertical asymptote, you want to simplify your rational function and find zeros of the denominator. Okay. So let's start really easy. If I have a function, a rational function such as 3x plus 2 over x minus 8, It's all already simplified. So my 0 for the denominator would be 8, because 8 minus 8 is 0. So my vertical asymptote will be the line x is equal to 8. And it's very important that you put x is equal to 8, that you don't just say the vertical asymptote is 8. Remember, the vertical asymptote is a line, so I need an equation of a line. X is equal to 8. Now, if I had something like x squared minus 9 over x squared plus 4x minus 21, you have to simplify that first. So the top becomes x plus 3, x minus 3, and then the bottom factors into x plus 7, x minus 3. The x minus 3's cancel, so you're left with x plus 3 over x plus 7. So you just find the denominator of the simplified rational function. So for x squared minus 9 over x squared plus 4x minus 21, you have a vertical asymptote at x is equal to negative 7. Okay. Now, one thing that I want to point out is if I ask you to find the domain here, the domain is still all x's, such that x cannot be negative 7 or x cannot be 3. Okay? You still have to use the original function, the not simplified version, to find your domain, but for the vertical asymptote, it's only the simplified rational expression, or rational function. Okay? So the vertical asymptote is pretty straightforward. Now we're going to go into finding horizontal and oblique asymptotes. Now before I get going into how to find them, let me describe what's happening when I have a horizontal asymptote. Right? If I have a horizontal asymptote, it's going to look like this, and basically my graph will look something like that. Now, the idea of a horizontal asymptote is that you're looking, so look at the graph, it's going to keep approaching this value. The value y is equal to L being some number. And if you really think about it, it's going to keep approaching it as x gets infinitely larger. So remember from the previous lesson that as x really gets larger, we talk about the end behavior of a function. So when we look at a horizontal asymptote, we're really looking for the end behavior of a function. So that's what we're really going to deal with when we're looking at horizontal asymptotes. So when we have horizontal or oblique asymptotes, there are a couple of scenarios. The first scenario, so remember, a rational function is p of x over q of x. And let's make this polynomial, p of x, start with am xm plus so it's basically a polynomial that has a degree of, actually, let me erase this because I want to make it consistent with what I gave the class. This is an xn plus an minus 1 xn minus 1 all the way to 0. Okay. Now, the second polynomial on the bottom, let's call this b of m xm plus b of m minus 1 x m minus 1 all the way until we have a constant. Now, this is just a fancy way of saying I have a polynomial on the top and on the bottom. On the top, I have degree n, and on the bottom, I have a degree m. So remember, the degree is the highest exponent in your polynomial. So we're going to look at different cases and talk about the horizontal or oblique asymptotes. So the first case is when the degree of the polynomial on the top is less than the degree of the polynomial of the bottom. Okay? So for example, if I have the function f of x is equal to 4x to the third minus 5x plus 2 all over 7x to the fifth plus 2x to the fourth minus 3x. Okay. Now, this is where n is less than m, which means degree of top is less than the degree of the bottom. Okay? The degree of top is less than the degree of the bottom. Now, if I look at this and I just want to look at the end behavior, the end behavior of the top polynomial is really 4x to the third. So this, we're approximating that the top approaches 4x to the third and the bottom approaches 7x to the fifth. Now, if we cancel that, if we cancel the x's out, I get 4 over 7x squared. Now think about end behavior. As x gets really, really large, that means my denominator is getting really, really large. And remember, in a fraction, when you increase the denominator, the number actually gets smaller, right? So 4 over 7 times a million squared is going to be a really, 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 really small number. So this number actually approaches 0. Okay? So whenever you have the degree on top less than the degree on the bottom, you always have a horizontal asymptote at y is equal to 0. No matter what, okay? This could be to the second power to the 10th, and this will end up as something over something to the 8th power, and that's still going to approach 0, right? It's because what's going to happen when my degree on the top is less than the degree on top, the degree on top is less than the degree of the bottom, you'll always have an x in the denominator. And as we approach infinity, right? So as we approach infinity here, this is going to be really, really small, so that approaches 0. So my horizontal asymptote is y is equal to 0. Now let's do a second case. The second case will be when n is equal to m. So for example, if I have 10x squared plus 2x minus 3 over 5x squared minus 8. Okay. If I want to find a horizontal asymptote, you see that if we talk about end behavior, the top approaches 10x squared and the denominator approaches 5x squared. The x squareds will cancel and you're left with 10 over 5. Now there's no more x's here. So as x approaches infinity, your answer is still going to be 10 over 5, which is 2. So your horizontal asymptote in this case is the line y is equal to 2. So in reality, whenever you have n is equal to m, all you really have to do is just take the coefficients of the first terms, of the terms with the highest power, and just divide them, or 10 over 5. Yeah, put them over each other, and if it simplifies to a number, you leave it as a number. If it's a fraction, you can leave it as a fraction. So if you want to see this again, so for example, if I have my function as 9x to the fifth minus 8x to the third over 27x to the fifth plus 2x. They both have, the highest degree is both 5. So my asymptote for here will just be the line y is equal to 9 over 27, which simplifies to y is equal to 1/3. Remember, it's a horizontal asymptote is a horizontal line, so it needs the form of y is equal to 1/3. Okay. Now, the next case is when n is equal, where n is equal to n plus 1. So for example, it's if I have 5x squared plus 3x over x minus 9. Okay. Now, we are not going to really go into detail here, but this is an oblique asymptote. And for now, we're going to skip it. We're not going to need it for this part of the class. But if your numerator is 1 greater than the denominator, you are going to have an oblique asymptote, not a horizontal. The reason why is, look what you have here. If you had 5x squared over x as your end behavior, you kind of get the line. Think about this as 5x, which you know is a line. That's not the oblique asymptote, but that's kind of, I want you to think about when you have the degree on the top higher than the degree on the bottom. The end behavior is going to approach a line. So, but we're not going to talk about that right now. But one thing that you do need to know is the last case, when n is equal to, is greater than or equal to m plus 2. Okay? So, for example, if I have 10x to the fifth minus 3x squared over 2x to the third plus 6x squared. Sorry. The end behavior approaches 10x to the fifth over 2x to the third. Look what happens here. The 10 and the 2 cancel, so I'm left with 5, and I could cancel out the x's, and I'm left with 2 x's on the top. So this is equal to 5x squared, and that is basically a parabola, right? It's going to act like a parabola. And remember, this is basically a polynomial function. When we graphed polynomials in the last chapter or looked at polynomial graphs, remember they had no asymptotes. So whenever the degree of the numerator is 2 or more greater than the degree of the denominator, there are no horizontal asymptotes. So whenever you are approached with a function and you need to find the asymptotes, you have to first find the vertical asymptotes and you have to find the horizontal. So let me do a problem in the book and let me go through how to find the asymptotes of that problem. Okay. So this is actually from the homework. I am going to do q of x is equal to 2x squared minus 5x minus 12 over 3x squared minus 11x minus 4. So remember, to first find the vertical asymptote, I have to simplify. So let me factor this. This is equal to 2x x, and then if I look at this, this should be 4 and 3 with the minus here and the plus there. Okay. And then the bottom factors to, that should be a 4, that should be a 1, I should have a minus there and a plus there. Now, if you look here, my x minus 4's cancel out. And so what I'm left with is I have the vertical asymptote of, what I do is I set 3x plus 1 is equal to 0. I solve for x, and I get x will be equal to negative 1/3. So my vertical asymptote is the line x is equal to negative 1/3. Now for my horizontal asymptote, I look at the degrees of the top and the bottom, and I see they are the same. And I have to look back and remember what happens when the degrees are the same. Well, all I do is I just take the coefficients. I take the coefficients and divide them. So my horizontal asymptote is y is equal to 2 over 3. And that's it. Okay? So actually, the concept behind it is kind of difficult, but finding the asymptotes, it's pretty straightforward.